Welcome, everyone. A very warm welcome to you joining us here today for the webinar, The Future of Atomic Layer Deposition, brought to you by ATLANT 3D. The field of atomic layer deposition is evolving rapidly, with innovative breakthroughs that redefine localized, sustainable manufacturing at the atomic scale. ATLANT 3D's direct atomic layer processing, or DALP technology, represents a paradigm shift in the thin film deposition by enabling high precision, maskless, and multi-material fabrication. Unlike conventional ALD techniques, DALP integrates spatial control, eliminating the need for photolithography and reducing processing complexity, time, and costs. This advancement accelerates materials discovery, device prototyping, and industrial scalability across sectors such as semiconductors, optics, energy storage, and quantum devices. This webinar we're having here today explores the benefits of DALP, including reduced material waste, faster prototyping cycles, and unprecedented process flexibility. By bridging the gap between research and industrial applications, DALP is paving the way for next generation electronics, advanced coatings, and beyond Earth manufacturing, positioning ATLANT 3D at the forefront of atomic scale innovation era. Before we get started with the webinar, we've just got a couple of housekeeping points to cover. You'll hear from Mira, Baraket, Head of Technology R&D at ATLANT 3D shortly. After the presentation, you will have the opportunity to ask your questions. You can do this by submitting the questions by clicking the Q&A section at the top of your screen. You also have the opportunity to tell us about yourselves at several opportunities via our polls, so stay tuned for them. Now, without further ado, I'm going to hand it over to Mira to start the presentation.
Thank you for the introduction, and thank you all for being here. I'm very excited today to talk about ATLANT 3D and about our technology. First, a quick introduction about myself. So I am a VP of Technology at ATLANT 3D. I have experience in advanced materials and in nanotechnology, and I've worked both in fundamental research and also on practical applications in energy and also in for bio devices. I've worked in different institutions. I can mention the Naval Research Lab and the French Atomic Energy Commission, but also I've worked in startups before, and this is my second startup. I'm working with ATLANT 3D. So really happy to have you all, and let's dig into the presentation. But first, as it was mentioned earlier, we will have a few polls in there. So I will need your inputs. So we will start with the first one here, which is I'd like to know more about your primary field of expertise. So if you can go ahead and select where your field of expertise is from. So I'll wait a few seconds before I continue or I start with the presentation. All right, so let's talk about ATLANT 3D. So ATLANT 3D has been founded in 2018. In few words, we are located right now in Copenhagen and Denmark. This is our headquarters, and major of the activities are happening. But also we do have a US and UK entity. We have also the support of many distributors across the world, and we have specifically in Asia, we have a few distributors that are helping our customers for the implementation of our technology. We are a team of 40 people. We have expertise mainly in material science and more specifically in atomic layer deposition. We also have a team that are targeting and focusing their time on many applications. So we have also expertise in areas of applications like optics, photonics, microelectronics, and in sensors. Also, we have a team of software engineers and system engineers that are working on producing our products. So, and of course, we have a sales team and a business development team and strategic growth team. So what is ALD and how? What is DALP and where it comes from? I'm going to start a bit to talk about atomic layer deposition. Our technology is based on ALD, which has been invented in the 60s and in the 70s, and this technology is based on reaction of two gases. So it's a deposition technique where you have to meet two different gases to create layers of material. But so the technique is a very conformal and it produces high quality only because the way that we are meeting those two gases or the interaction is happening on the surface. So instead of having the gases meet or the two reactant meet in gas phase, you would have to go through a sequential pulse process that will enable the deposition or the reaction to happen on the surface. So the way it works, you would send your first gas onto your substrate, and then before you send your second gas or the reactant, you will have to have a process which we call a purging process that will enable the cleaning of our process chamber. So if you were to go through the process one by one, you send gas one, then you would have a pulse or a purging process, then you go to gas two, and then again you go through another purging process. So the way that I'm explaining it is a long process, as you are hearing, and this means that in the industry this was one of the major drawbacks of this technology. So although it really had brought a very high quality of films, but this has hindered the ALD technology to be widespread or highly applied in different industrial applications. But later on, spatial ALD came in, and this technique, what it's bringing to the ALD, is that instead of having a sequential and temporal approach, now you are having all of the gases flowing all at the same time on your substrate, and now instead of changing and opening valves, it's your substrate that now it's going from two different regions or from two different sections. So the two gases that the regions that you are using in this case, they are separated by a shielding gas, and then the substrate, as I said, is moving from one place to the other to be exposed to those two gases. So the quality of the material is the same as in ALD, but now you have a much faster process. And this was brilliant as it has enabled ALD to be used much more widely in microelectronics. Now, what ATLANT 3D have done is to take that concept and to shrink it down. So now the precursors are now delivered on the surface in the same way it is done with spatial ALD. And as you can see on this schematic, all the gases are delivered on a very small surface, and the substrate would be moving underneath. What's different from spatial ALD is that now we are depositing, or we are having the process localized partially on the surface. So you can enable processing for like direct patterning or direct processing on your surface. And the way we do this is through our micro nozzle that you can see it here on this slide. So our micro nozzle is customizable and it's scalable. So you are able to change the different to change the size of the nozzle, but also to change its geometry depending on the application that you are looking for, and depending on the size of the pattern that you are looking to deposit. So our technology, or this micro nozzle, has been patented, and we do have several patents already granted, and across the world, and we are constantly working on protecting our technology, either on the micro nozzle side, but also on some application side. So we are constantly working on that on application of patents as well. So the reason we have come up with this solution, it is if you were to think about the traditional lithography-based micro and nanotechnology processes, this would have to go through a very lengthy processes that have hindered a lot of the innovation cycles, or have hindered the innovation cycle from being it fast and as you can see on this slide here, so if you were to go through the photolithography steps, you would start with a wafer, then you have to go and create a photomask before you can go. You go through the different exposure steps and development, and then you have to reiterate through all these processes. So these processes are usually done with different machines in the clean room, and so you have to twiggle between the different machines, but also the different processing techniques. So what this means is that you have to have a very expensive capex and opex, and also because of the high need of these different processes and the skills that are needed to go through all of these processes. This means that the innovation cycle is very slow, and there is limited number of materials and processes that you can use because of the dedication of each of the tool to each of those processes or the materials. And finally, because you are going through those lithography steps and where you go through a resist removal and lift-offs, this is ecologically harmful and it has produced a lot of waste. So what we are bringing with our technology is not only about deposition, but it is also allowing to enable locally multiple modes of processing. You've heard me talk about ALD at the beginning, but when we talk about DALP, we are talking about different processing techniques. So not only deposition, but also etching, doping, and cleaning. So what this means is that now you have with one tool, you and with one micronozzle, you are able to have direct additive or subtractive processing techniques, but also direct doping and direct deposition or structure, 3D structure growth. Now I'm gonna ask you a second question here. So if you can also respond to the second poll about your familiarity with atomic layer deposition. Okay, then so then now I'm gonna continue my presentation. As you've heard me talk about the different modes of processing, this means that instead of using the different microfabrication technique and processes that are usually used with the photolithography steps or with the standard processing techniques, now we are enabling all of these processes is in one tool. And I would like to talk to you today about our nanofabricator light, which contains our DALT module, and with the different automation and controls and the gas system, now we are enabling an easy way of the digital manufacturing. So what does this mean? With one tool, all what you have to think about, or the most of the time that you will have to spend, would be on the design of experiment. So you would start by bringing the design that you would like to print or to process. Then you'll have to prepare your nanofabricator by filling the materials and by loading the samples. And after that, you go through the definition and the design of the parameters. So there is practically we have a software in our nanofabricator that will allow you to import your CAD design, and you will be able to see and to simulate how the output would look like. And so through that process, you can still do some edits and refine your parameters and the position of the processing that you are going through. And then you would launch your job, and then you will have your job will be printed, and once it's done, you will come with either a material or a process or a device that is already fabricated by using our tool. So the technology is it's not only about device fabrication or about prototyping. It is actually enables a lab to fab across the whole value chain. So you can think about accelerating materials and process innovation, or you can enable micro device and prototyping, but also in the manufacturing. We have targeted our product roadmap, so you can enable also practically applications manufacturing platform that are designated for your specific application. So what this means that with our technology, if you were to compare with the technologies, the standard processing technologies, now we have reduced several of the steps in the process. So this means your innovation cycles are much faster. We have an end-to-end process with much lower steps. That also it means that you are reducing your cost. And finally, it is a very sustainable process. You don't have to go through the post-processing steps and you are using much lower number of precursors or or chemicals. So you can end up creating complex patterns and all of that with multiple materials, and these can be directly processed within a systems on your wafers. So in terms of sustainability, you've heard me say that we are also reducing waste. There is one main reason I can say that not only because of we are eliminating the lithography and the post-processing steps with our direct patterning approach. Our nanofabricator system possesses a unique gas system that would allow us to supply only a small amount of the precursors. So this is one of our know-hows. As opposed to the traditional ALD, which requires much higher volume of precursors. So I'm going to ask you a question related to the sustainability. How important is sustainability in your manufacturing decisions? This is our third poll for today. Okay. And in my next slide, this slide, I just want to show you, compare our technology in particular with ALD and with other direct printing techniques, like for example inkjet, and also I want to compare it with lithographies, as I have been talking about it throughout the presentation. So in terms of precision, ALD and DALP both are bringing atomic precision. So we are able, because of the process and the way that all the gases react together, the deposition is controlled with high precision in terms of thickness. If you were to think about inkjet printing, this is more on the nanometer side at its best, and more often it is more on the micrometer size side. In terms of for the lithography, this is more. It is not only about one technique, so this is all dependent on the different processes and techniques that are used. So if we were to compare, we should compare with PVD or CVD, and in that case, the precision is much lower. In terms of resolution of the depositions or the patterning, the resolution patterning, we were able to go below 100 micron, but also as far as 2 micron in terms of resolution, which is comparable to that of inkjet printing as well. In terms of material, this is where ALD and DALP brings its versatility or its outstanding performance. If we were to look into the number of materials that can be done through ALD, it is exceeding 400 materials, and it does not stop there. There are a lot of ways to create new materials with specifically with DALP. If you were to compare with inkjet, it is very limited in terms of number of materials because of the inherent property of the technology. And for lithography, again, you have to switch between different techniques for manufacturing to be able to expand the number of materials to be deposited. In terms of scalability, from our side, we have a roadmap of products that will allow you to scale the manufacturing process from prototyping up to high volume manufacturing, and this is lower the case in inkjet printing. Of course, as I have showed you earlier, we are integrated across the whole value chain. And in terms of time for completing a development of a new material or a new innovation, the time that you would spend with our DALT technology is much, much lower compared to ALD in general, but also the other techniques. So in practice, what materials can we deposit with direct atomic layer processing with our technology? So we have so far tested many materials, and mainly I can say what you can see in the list here: oxides and metals. And I would cite specifically platinum, titanium oxide, tin oxide, zinc oxide, and aluminum oxide. And we are constantly working on introducing much more materials into our validation process, and also I'd like to mention that we have validated already sulfides and fluorides, and we are constantly working on improving the technology. So we will have soon an upcoming process that will enable us to also bring nitrides to the list of materials, among others, of course, and I'll be talking more about those in a few slides. For now, I'd like also your inputs on which emerging materials are most relevant to your research or for your manufacturing process. So I will wait for a few seconds for you to respond to this poll as well. All right, so this brings me to my next topic, which is about the resolution size that we are able to achieve. In 2019, when the technology have proven its first proof of concept, it was done with a 400 micrometer lateral size resolution. So our nozzle, as I mentioned earlier, these are customizable. And then we have done some progress, and in 2020, we were able to achieve 250 micron. And then with different processes and understanding of our process, we were able in 2022 to introduce a few steps that allowed us to go as low as 5 micron in deposition resolution. And recently, we had a breakthrough in our technology, where we were able to introduce a new nozzle type that will allow you to have a variable line width with one same nozzle. So what this means is that you can also create your patterns, and you can have different line widths of your patterns on using the same wafer, or using the same wafer using the same micro nozzle. And we are constantly working on improving our resolution, and it's something that we do have processes and technologies that we are confident it will allow us to go beyond the 1 micron resolution. So what does it mean? What it means also, if we are able to directly pattern on a surface, it's not only that you can create a device with multi-materials, but also you have now a new way of surface structuration. Here is an example of 3 different types of structures that are created because of the direct deposition method or direct processing, either by the deposition or etching, and I will talk about that in a bit. On the top here, it's a staircase that have been created with 0.2 nanometer step height and with a 3 micron step width. In the middle, this is a few valleys that have been repeated with 1.5 nanometer of height. And on the bottom here, this is a structure that is very hard to be done using standard methods of manufacturing. So we have created a tapered shaped structure. This is a structure that is done with multiple thicknesses. If if you were to think about doing this using your normal deposition techniques or your normal processing the techniques, so this would be very long to do, or if not impossible. So we are also with our technique. We also work on the alignment and precision and the uniformity of our deposits. Since we are creating some devices, this means that the deposition can sometimes be done in alignment with other pre-existing patterns. That's why it's very important to have an accurate alignment, and we are able to achieve an accuracy of 1 micrometer. In terms of precision and repeatability of our deposition process, we constantly have processes and continuous quality control, and we are able to get to a deviation of the process as low as 1%. So of course, this is dependent on what material you are depositing, what substrate you are depositing on, and the nozzles that you are using. So these numbers are only for one material with one same nozzle used all at the same time. In terms of the material uniformity, this is also that we have a high degree of uniformity on of the deposition of the deposited material, and we are typically better than 1%. So the process, again, I would like to go back to the DALPA process. It's not only about deposition, it's also about etching, about creating ternary materials, and about multi-layering. So in terms of materials, as I've showed you earlier, we have already qualified metals, oxides, sulfides, and fluorides, and we are looking into incorporating more. And I would specify nitrides, which is one important material that we would like to introduce soon. Also on the etching side, we have confirmed and demonstrated etching of zinc oxide and aluminum oxide, and more are to come soon. We are in the proof of concept phase for making ternary materials, and we are interested in the materials that are listed here: aluminum zinc oxide, lithium niobium oxide, and hafnium zinc oxide. Multi-layering, of course, is inherent to our technology. So it is something that we can do with all available materials. We have already validated titanium oxide and magnesium fluoride, and also we've validated more materials that are based on aluminum, platinum, and others. So now I'm going to go to the next poll here, and this one is about the selection of thin film processing technologies. Which factor is most important to your business? Okay, thank you. I will move to the application. Where is our technology used? And I will show you a few use cases. In terms of application, we have a large span of different application interests from different industries, and I can mention in optics and photonics a lot of interest in optical filters and in waveguides. In microelectronics and power electronics, we have a lot of interest from the MEMS and sensors, and also for local passivation and etching in the semiconductor and in advanced packaging. And emerging technologies, I'd like to mention neuromorphic, where we have a very good alignment in terms of the needs and where we are bringing solution to this particular application. And of course, we have a lot of impact in fundamental and industrial R&D, either with new material innovation or new processing, but also in new device structures. So we have, with our technology, we are enabling the complex patterning of multiple materials. These are examples of what we have patterned and what we have deposited on our wafers, but I'll go through more in detail on some of the example of some use cases, specific use cases. So in terms of in material properties, or in the if we were to look onto the value chain, we have what DALP enables. It enables a rapid design of experiment for different material processes. So if you were to think about an application like optics or photonics, in these cases you are looking to find an optimum material condition, and to do so with our technology, you can think about taking you can design your experiment in a way where you take your wafer and you will have you can deposit multiple a numerous number of materials, or a numerous number of process conditions. So in this case, we are talking about titanium oxide, where you have your we take our wafer and we have deposited multiple lines with multiple thicknesses in the rows that you are see here, and but also we have processed our material at different temperatures. And what we have ended up is with that technology, we were able to have an efficient development process. So we were able to get 50 data points of titanium oxide that are generated only just in 6 hours. If you were to compare that with normal technologies, then this would have been taken 1 or 2 weeks using the conventional methods. And here is an example about rapid process development and prototyping. This is the case of high-performance thin-film transistors. So we have a pre-deposited contacts on the surface, and what we have done with our technology is that we were able to deposit zinc oxide with different deposition conditions, and now you have a readily available wafer with multiple prototypes of different materials or different material conditions of the transistor. So we were able to deposit 24 different deposition conditions of zinc oxide in this case within one single day. So again, if you were to compare and to go through a normal processing techniques, this would have taken 2 to 3 weeks. As the technology is based on ALD, conformality is really one of the highest interests in the technology, but not in the same way that it is done usually. So if you were to take ALD, yes, it is very conformal, but if you were to use normal ALD and on irregular substrate, on substrates that are not flat, then going through the different processes and the different techniques for creating patterns would be very troublesome, because those techniques are only work well with wafers, but they don't work well when you have corrugated surfaces. So what we are enabling here is the conformality of the position of the coatings, but also selectively depositing on the surface. The examples I am showing you here are for deposition on different types of corrugated materials. On the top left, we are showing the anodic aluminum oxide that are coated with platinum. And on the right here is another material, another structure, which is a black silicon surface that's coated with platinum. Also in trenches, this is also something that is usually difficult to go through selective deposition with the normal techniques. And with our technique, you are able to deposit conformally, but also directly on trenches, and as can be shown in the two bottom pictures. So in terms of processes, this example is about local edge passivation. This technique have been used for solar cells, and DALP have been used to passivate the edges of the corners of silicon chips. And what you can, if you were to try to do this process using normal or using standard processing techniques, this would be very difficult, and you would struggle with the deposition on the edge of a surface, because you would have to go through the etching and of the front and back side of the wafer, and this would be very costly and time consuming. So in this case, what we have been showing that we were able to improve the carrier lifetime after the edge passivation only on the surface, and this was done only by depositing within few hours of deposition. So the next case here is about chip surgery, and this is very important in microfabrication, where sometimes minor deposition errors can bring significant cost, indirect cost problems, I would say, into the microfabrication process. So in order to reduce the waste and to reduce the time, you are able with our technology to, you can scan the surface and then you can inspect it. And if you were to see any anomalies, these you can instantly draw and patch the surface. And then after your processing or the deposition, now you can inspect again, and you are able to look into the surface and to create a continuous deposition. In this case, it was platinum. So this is a really nice case where you're reducing the cost or you're reducing the cost in time, but also in terms of sustainability, by creating those quick and patch creation on the surface. So here is an example of a device example. In this case, we have created multiple capacitors. This is a metal insulator metal, and what we are trying to do is have a rapid design of experiment. So we are scanning between different deposition processes to be able to find the optimum conditions or the optimum capacitor in our case. So on the top here, what you can see is a heat map of a capacitance versus dielectric thickness. So you can, after the depositions that are done with DALP, now you are able to characterize the surface, and you can quickly have select your optimum characteristic or characterization processing. Your optimum processing conditions. The same on the bottom. So on the top, what we have changed is only the dielectric thickness, and on the bottom here, we've changed the dielectric thickness, but also we have used different deposition conditions for the top electrodes. So we are not only changing one parameter, but also we are changing multiple parameters, and this is brings a lot of faster, I would say it would bring a faster iterations for innovation. So direct processing of multiple material devices, this is inherent to our technology, since you are directly patterning onto the surface, and you are able to create, to deposit multiple materials. These are examples of deposition of multiple metal insulator metal capacitors. One of them actually is the metal insulator metal capacitor, but also we have added electrochemical sensors and other sensors like the platinum and titanium oxide surface sensor. So as you can see, these are all printed on the same device, and the deposition time in this case for the creation of the whole sensors was within 30 hours, 34 hours. So this is another example about the conformality of the deposition, and where DALP technology has brought a solution to a problem that you can see in microfluidics. So if we were to to process sensors and microfluidics, there is a big problem or a limitation in terms of patterning on again non-even surface. So in this case, you have geometries like 90-degree walls and trenches. These are not compatible with the standard fabrication processes, and with DAO technology, you are able to directly deposit inside those channel floors. So the case that I'm showing you here is about is the microfluidic channels that are 100 micrometer wide and 40 micrometer deep. And we were able to deposit conformally the sensor even across the 90-degree vertical walls. So I think this will be my last application slide. This is one example where we have brought a solution in MEMS and in optics. This is the example here that we are having a chip that's suspended. And again, this is very difficult to process in a normal, in a standard processing techniques. And with this case, we were able to deposit a protective layer on the structure without altering the properties of the device itself. So in this case, we were able to make this deposition within a few hours only. So now I will again seek your attention for another question, which is about the next generation manufacturing solution and what are the preferences that you would have. Okay, so this brings me to our product map. As we've said, I said earlier, our technology is a lab to fab solution across the whole value chain, and we have multiple products in our roadmap that will enable the technology to follow the innovation cycle from material process to prototyping and also to manufacturing platforms. I can mention here that the different in our roadmap we have different products that in each of those products we are enabling the manufacturing for different wafer size or coupons. In the case of the Nanofabricator Lite, with the Nanofabricator Pro, we are enabling manufacturing. We are enabling industrial R&D and a small manufacturing production. And so in the case of the Nanofabricator Pro, we have the wafer size of 4, 6, and 8 inches. But also we are thinking about the long term. Our Nanofabricator is enabled to be connected with a cluster tool, and this is the case of the Nanofabricator Lite. And also on the in terms of application specific, we have the Nanofabricator Flow, which enables the fabrication of an application-focused fabrication where you can combine several digital fabrication and manufacturing tools in the same platform. So in terms of business model, we of course sell our nanofabricators and equipments, but also we work a lot with our customers on innovation as a service. So we do run a lot of pilots and R&D services and joint development with some of our customers. On the long term, what we are looking to enable is again increase this or having a faster innovation cycle by and this would be only enabled if we were to create an A-hub where we have our different manufacturing tools and characterization tool that will enable different the researchers but also industrials to use the tools from R&D to prototyping up to manufacturing. So this is all comes with our vision to drive the atomic scale manufacturing. We are looking to expand the market, the application market with the different products that that we are bringing. Our modular platform enables compatibility with other deposition techniques or other processing techniques. And with our hub, we are looking into creating a network for more like an innovation center network. So with that, I would like to thank you all for your attention, and I will be happy to take all of your questions.
Thank you, Mira, for that great presentation. We're going to have some questions now. Just a reminder that you can send your questions in. If for any reason your Q&A isn't working, feel free to send the questions over in the chat and we'll get those answered for you. Just another reminder before we start the Q&A, you can contact ATLANT 3D if you want to know any more about the technology or the product by visiting the ATLANT 3D website and going on the contact section. So let's kick off with the first question, which is, are all ALD precursors compatible with DALP technology?
Yeah, thank you for the question. So most of the materials that we have deposited are used are done using normal precursors that are usually used for ALD. So our gas system do require some specific like range of vapor deposition and temperatures, but we have collaborations with different research institutes that were able to produce for us some alternative solutions. I can cite, for example, zinc oxide. We have been working with specifically made precursor that made this material compatible with our DALP. But I would say in general, 95% of the precursors of ALD can be used with our DALP.
The next question is, are there any intentions to develop metrology solutions for DALP?
Yeah, so since we are talking about DALP as a module, this is definitely something that we have already thought about, and it's something that have been introduced within one of our systems. I can think about we have one nanofabricator flow where we had integrated a optical characterization solution with our DALP. So yes, this is absolutely something that we do when we create the nanofabricator fabrication platform for a specific technology. And in our hub at ATLANT 3D, we do have many metrology solutions that we use to constantly control quality.
And the next question is asking about aspect ratio in DALP.
Yes, so the aspect ratio, absolutely, it's very important. We are working into looking into the limitations. But so far we were able to deposit in trenches that are as long as 200 micrometer. But in terms of aspect ratio, I don't have the exact number. So we can, of course, follow up on that, and it's something that we are looking into.
How long does it take to realize a device?
So this is dependent on the device and the complexity of the structure that you are looking to add or to make. And also it's dependent on the material that you are depositing and on the thickness of the material that you would like to deposit. So the way that we like to think about it's more about the end, about the time of processing that you would have taken to create several prototypes. In that case, you are reducing. And in terms of time for fabrication of one single device, this can be, of course, calculated, but also it can be multiplied by several, or the throughput can be increased depending on the DALP technology or the nanofabricator that you are using.
And typically, ALD machines are operating under ultra-high vacuum condition to avoid contamination via metal organic precursors. How do you deal with this issue, as it seems you are not having a high vacuum chamber?
Yeah, so that's correct. We are operating in atmospheric pressure, and to avoid contaminations, we do have different nozzles for different materials, but also we have different processes of purging throughout our gas system to reduce those contamination risks.
And we've got a question here. How about the deposition with angled, say, 45 degrees, 1D or 2D structures?
So 90-degree was one of the most difficult one, I would say. So if you are talking about 45 degrees, in our case, so we have some solutions where we can bring to deposit or to process angled structures. And if you recall that we are not only about temporal deposition, we're not only about spatial deposition, but also we can create a modes of temporal deposition where you are now more closer to the normal ALD mode. So these structures would are probably are of course challenging, but there are solutions for that with our different nozzles that we have created.
And how does DULP address the challenges of high material waste and energy consumption commonly associated with traditional atomic layer deposition technique?
Yeah, so in terms of material waste, in all of our processes, actually, the precursors and the gases that are used, they are heavily diluted. So we are talking about a very low percentage of precursors. And also we are only depositing locally on the surface, which means that all of the steps that are required with the standard techniques are not there anymore. And this is how our consumption of I would say overall for making a device, you are not only reducing waste, but also you're reducing the energy consumption as well because of the reduced number of steps that now you go through.
We've got another question here. What are the challenges of using DULP in gate-all-around transistor fabrication?
Yeah, so for that question, I would be happy to talk more, probably have a discussion about that. We have already started working on specific applications related to to transistor applications. So I think in this case, I would go through a private discussion. This way we can address the different concerns, or we can also show some materials that we already have.
And is it possible to develop 2D materials like graphene using this technique directly on a desired substrate?
Yeah, so in terms of 2D materials, yes, we have already shown the deposition of 2D materials, but not graphene. I think a graphene is a specific case where you require a much higher energy to deposit, and this is not compatible with ALD in particular, but in general, if you can think about boron nitride or dichalcogenides or other 2D materials, these have been already processed and proved. So any material that you have seen that have been done already with atomic layer deposition, these are transferable to DULP as well.
And is the machine clean room compatible?
Yeah, so the machine does not require a clean room per se, because it's the way that the process works. It can work in an environment, open air environment, but of course it is compatible with clean room if the processing or if there is need for the machine to be in clean room. Yes, it is compatible. So we have created an upgrade, or one of the options for our nanofabricators is to have a environmental chamber. In that case, with this environmental chamber, you can also have a full control over the surrounding environment.
And how are you ensuring the thickness of multiple depositions?
So the thickness control is always based on each material that you are depositing. Usually we go through a processing and qualification process that will enable us to know the deposition or the growth rate. So then that would be later implemented into the software, and it can be translated into the simulation. So these are all inputs that has to be either they are already in the tool because of the we have already used that material, or they can easily be drawn out from few processing of the material.
Are there any adhesion problems in DALP? How are you tackling adhesion problems with flexible substrates?
So I would say that to answer this question, it is as close to ALD. When you see any problems of adhesion with normal ALD, then this would possibly happen with DALP, but usually we don't see those problems. I cannot recall one case where we have an adhesion problem. And if it's the case, there are, like in normal processing techniques, there are always pre-treatments that can be introduced. But I would say there is no difference between DALP and ALD, so it's not producing any more adhesion problem than what's usually happening with ALD.
And someone is asking if DALP can be used in the selective etching of 2D materials for precise patterning in semiconductor device fabrication.
So I think this depends on which 2D material we are talking about, but of course we are open to a discussion about that. So if you can contact us privately, and then we can also have a discussion about the specific materials you are thinking about.
And finally, are you working with any research institutions or universities to expand DALP applications?
Yeah, of course, and I would open this announcement here as well. So we are open to exploring different activities and different applications. So if you have any depositions, or I would say processing in mind, or applications in mind, please reach out to us. We would be happy to collaborate. We've already started the numerous number of collaborations with different partners around the world.
Perfect. Well, I think we've answered all of your questions here today. So I'd like to say thank you again to Mira and to everyone attending for your participation, both in the polls and in the Q&A. Like we've already said, you can contact ATLANT 3D for more information on the technology. But yes, any final thoughts, Mira, from you before we leave?
No, I'd like to thank you all for your contribution. This was I think we will have a continuous number of webinars that will be upcoming, and so please stay. Have a look always on our website, and you will potentially, I think, get newsletters about the upcoming webinars. Thank you all for your attention.
Thank you. Bye, everyone.
Thank you.